Hi, this is Ricky Stevens, and this is my update on my coffee mug optimization project. So just a quick review on the project topic. We're looking for the optimum mug shape that will minimize the heat transfer from the coffee to the surroundings. The design variables will be the thickness of the slices, DZ, and each radius, RI, where each radius will vary linearly from one slice to the next. The objective function, which we want to minimize, will be the total steady-state heat transfer rate from the coffee to the surroundings. We will formulate this using the thermal resistance model. Since the project proposal, I have defined all the necessary parameters I need to solve this problem. This includes the volume of coffee that the mug holds, the coffee temperature and the temperature of the surroundings, some of the dimensions of the mug, and the thermal coefficients. These are the constraints that I've defined for the problem. The volume constraint is an equality constraint, while the rest of the constraints are inequality constraints. The open top constraint simply makes the top of the mug wide enough so you can drink from it, while the stability constraint makes the bottom of the mug wide enough so that it won't tip over easily. The inward overhang constraint limits the slope of the mug so that it can't overhang in the middle too much, which will make drinking from the mug easier. Lastly, we have the bounds on the design variables. This is the thermal resistance model that I have formulated. You can see that I consider the convection, conduction, and radiation from all sides of the mug. I also noticed that all mugs have this ring on the bottom to minimize heat transfer to the table. I also decided to include this in my calculations. At the bottom is the equivalent resistance of the circuit. Here are the formulas for the resistors, along with a description of each resistor. You can see that the resistance value is a function of the area through which heat is flowing, and also some thermal coefficients. These are the formulas for the area through which the heat transfer is taking place. They are functions of the design variables. These functions will be inserted into the resistance model. Now, what still needs to be done in the project? I will enter all this information, including the objective function, bounds, and constraints, into MATLAB. I will then solve the optimization problem with only a few slices to start and plot the mug shape. If this is successful, I will move on to more slices and see how the design progresses. I will validate the assumptions made in my model using an FEA software. I will compare the heat transfer rate for a standard cylinder mug using my assumptions and using an FEA solver. After finding the optimal mug shape, I will again compare my result for the heat transfer rate with the results of an FEA software. I will lastly consider extending the project by allowing voids in the mug wall or allowing a variable mug thickness.